Hello and welcome to Some Assembly Required. This video is part 4 of 3 of implementing the rotate left instruction, which is strange because in the previous video I promised you we were done. However, if we look at the opcodes, we've only done one opcode, the one for absolute addressing. There are other opcodes for absolute addressing plus x, 0 page plus x, and directly working on the accumulator. If we want to say that rotate left is done, we need to do all of those as well. Unsurprisingly, the place to start is with the test program. We left off at 840 where we placed a no operation to signify the end of the test segment. However, obviously, it's not the end if we're not finished. So let's start adding the other opcodes. Let's start with 3E. So 3E, that addressing mode is absolute plus x, so it needs 2 bytes for the address to which we add x. So that will be 0000, and we'll get back to it. And the address here is, of course, 0840, and that's rotate left something plus x. What should that something be? Well, I'd like to rotate the same address again. In order to do that, I need to write here an address that plus x will be C7F4. So let's go to the simulation and run it to its conclusion. We don't care about the failure. The failure is because we changed the program without changing the test plan. What we do care about is checking what x and y have. So x has 2, 5, and y has 8, 0. Those are the values we need to account for. Let's go back to the memory. So we want this value to be something plus 2, 5 equals F4. So that's F, that's E, minus 2 is C. Let's see if I got it correctly. We want C7CF plus 2, 5, C7F4. Yep. So that value is C7CF. Now, unlike here where the carry was clear, the carry here was set. So we want to see the value rotated in have the carry set. Likewise, the value we rotate out here, if you'll recall, was 2, 8. Which means that another rotation will bring us to 5, 0, actually 5, 1, because the carry is set and it will rotate in a bit 1. So that will be the value we rotate in. Let's put that in the expected results in our test plan. We want a write command that will take, we need to check how long it should take, right? So addressing mode. We want the absolute plus x. That should take 4 cycles with the usual 1 and 3 footnotes, with 3 being relevant for us. Read, modify, write, add 2 cycles. So 6 cycles. The opcode is 3E. It's read from 0840. And it should write at the end 5, 1 to C7F4. Now for good measure, let's add some branch. So let's decide which flag we want to test here. Our rotate left is affecting the carry 0 and negative flags. Let's test the negative flag first. So branch minus to, let's say we branch to 083F. We're not going to be taking the branch anyway. So to 083F. Branch minus is 30. And the next value is this address. So that's 0845. This address minus this address. So 083F minus 0845, that's FA. It's a negative number, but that's the way we represent it. So next we expect at 0843 to execute opcode 30, and it should take 2 cycles because the branch is not going to be taken. And last data on bus is irrelevant, we're ignoring it. And the next address to read from is 0844 because it's only 2 cycles. The first cycle will read the opcode, the second cycle will read the operand, which is the relative address to jump to, and the third cycle is already the next instruction. And this one will be 0845 and 0846. So that's our test plan. I spent quite a while on the first video until I figured out that I need to actually close the simulation and relaunch it whenever I change the memory or the test plan. So close, reopen, yes, I want to relaunch, run, and we fail, which we expect to, because of opcode shorter than expected, and that's the opcode we just added. That's 3E, so far we're fine. So let's implement opcode 3E. We want the decoder, and we want 3E. Uncomment it out. Since I wrote all of the opcodes down, I changed the order. And here's where the magic happens. What I do during this decode, and I'm getting a lot of flack from people who actually program FPGAs for doing this, is that I'm splitting the opcode into 2 parts. So I'm decoding it into which operation needs to be performed and which addressing mode needs to be done. By this split of the state, I'm achieving actually more than one thing, but the thing of note here is that if we've already implemented the operation for rotate left, and we already implemented the addressing mode of absolute plus X, uncommenting these 4 lines is all we have to do. Let me show you. Reload, run. Simulation successful. That was too easy, right? So let's go back and verify. Here we are at address 840, reading the opcode 3E. Next, we're reading from 841 CF and 842 C7. And the very next instruction, we're reading from C7F4, the value 28, which is what we wrote in the previous run. Second cycle where we do the ALU. And third cycle where we write 5.1. So in all of what? 5 minutes, we've written the test program, the test plan, and implemented by simply uncommenting a bunch of code. We literally spent more time writing the test program than we spent on implementing the actual opcode, because we already spent 3 videos doing so. That being the case, let's quickly go over the rest of the opcodes. Opcode 2.6, addressing mode 0 page. We can't use the same address because it's not in 0 page, so let's pick an address in 0 page. Let's pick an initial value that will exercise flags we haven't seen in use so far. Update the test plan, run the test, it fails. Update the decoder to set the correct operation and addressing mode, run the test, it passes, next. Opcode 3.6, addressing mode 0 page plus X, reference the same address as the previous one. Write the test program, this time expecting a 0 result. Update the test plan, run the test, it fails. Decode the operation and the addressing mode, run the test, it passes. As you've probably noticed, I'm starting to move a little bit faster when I'm covering things we've already done before. If you think there's anything unclear or you don't understand, please leave a comment in the comments section below. Also, I would really appreciate it if you press the like button. Just one more to go. This is the rotate left of accumulator. Let's see what the accumulator has right now. The accumulator has F7. I say we roll with that. So the accumulator has F7 and the carry is set. So we need F7 times 2 is EE plus 1 because of the accumulator EF. Right, so 2A, and that's it. That's all the bytes in the instruction. 84D, rotate left, and that's 84E. No, sorry, before that, first thing we want to do is make sure that the accumulator has the correct value now. So what we'll do is we'll write it somewhere, because unlike the rotate left directly from memory, this doesn't expose on the buses what happens in the accumulator. We don't know that the value is correct after the operation. Remember that unlike the simulation where I can ask to view any value I want, the test program can only see what's outside the CPU, what goes on the bus. So we'll do store A somewhere. About store A in the test program. Again, I'm skipping over the details of typing out the program. I think it doesn't add any value to what we've seen before. Instead, I'm skipping right ahead to writing the test plan for the rotate left instruction itself. How many cycles should it take? Addressing modes. Accumulator 2, to which we need to add read, modify, write. No, wait a second. This one does not have footnote 3. It takes 2 cycles. Obviously, we will need to do something different here than we did before. If we look at the opcodes, we've seen that we pretty much were breezing through the various variations of the rotate left, and all of a sudden 2A is sort of giving us some grief. So what we'd expect is to go to 2A, uncomment, replace those 2 lines, and then do some sort of setup address accumulator. However, there is no set address accumulator. And that makes sense because if we look at the implementation, we can see that just the operation part takes 1, 2, 3, 4 cycles. And we need it to take 2, which means that we need an entirely different operation for that. So instead of rotate left, which is just rotate left, we need a rotate left immediate, which will be 99. And we need to handle that differently, which is kind of a bummer, but that's also what the original 6502 did, so we'll just have to live with that. So what do we need to do here? I think we can start by copying our previous implementation of rotate left and start off of that. So here we go. First thing, we need to set the correct operation here. Also, we're going to set up a different address. We're going to set an implied address here. You will notice that this will fail because the implied address needs a parameter with the name of the operation. So we need to call it like this. So that's the first step. Let's see what we do here. First of all, this is fine. This is the first cycle. And the second cycle is this one. So anything after this just doesn't take place. So right off the bat, we know that we need to call next instruction here. The good news is that we do not need to fetch anything from memory. So we do not need this line. Since this isn't a read, modify, write instruction, we do not need to set the memory lock. So these two are eliminated. Instead, we see that we need to set the data bus source. So we need to set basically the same signals, the same control lines as we did before. So we need to set the data bus source. We need to set the ALU op, the ALU carry source, and the ALU B source. Except the data bus source isn't the memory, it is the accumulator. So these should be enough to make sure that the ALU is now performing the operation on the right value. So this cycle is pretty much covered. On the second cycle, we don't care where the data bus source comes from, but we do need to set the control signals as before. One more thing, we need to update the accumulator. So I was wrong about not caring where the data bus comes from. We do need the data bus to come from the ALU. So this is... So the data bus comes from the ALU, and we need to update the accumulator, and we need to update the carry, negative, and 0 flags. That should do it. Let's see. Assuming we compile, that is. Right, data bus source, it doesn't know what that is, which means that I misspelled something. Data bus source, ALU reg accumulator. Let's see if we're now better. The simulation is successful, but we're not really done because the flags aren't set correctly. So we need to set those before we can call ourselves complete. We see that the negative and 0 flags are read incorrectly. They are updated in this cycle. They should be updated from the ALU result. So that's here. So yes, we need to do that one cycle earlier than we have. We need to do that on the first cycle rather than the second cycle. Let's see if that's possible. So this should fix this. Let's see. Yeah, the flags here are correct. So yes, we are done. Let's update the green marker here to A. And the next step is, so I usually like to do git add -p, which allows me to check individual changes. Okay. So, opcodes. 2E existed before, so 3E, 2A, 2.6, and 3.6 rotate left is done. Done! As before, one more thing to do. 3E, 2A, 2.6, 3.6. Done. So there you have it. We've finished implementing rotate left with all of its variants. Next video will be part 5 of 3. Ooh, we're actually switching to a new topic next video. We'll be improving our test infrastructure so that writing the tests will be less annoying. We'll also be doing stuff with this. I think it's cool and I hope that so will you. So until next time, thank you for watching.